So this is the first video for Chapter 4, which is called Reactions and Aqueous Solution. Chapter 4 is very much a continuation of Chapter 3. So just a quick reminder, in Chapter 3, we learned how to balance chemical reactions, like balance chemical equations. We learned 3 different categories of chemical reactions, so combination, decomposition, and combustion. We also learned 3 unit factors. 1 mole equals Avogadro's number, which is 6.022 times 10 to the 23rd things. And we use that unit factor when we're counting the number of atoms or molecules we're looking at and group them into how many moles of atoms and molecules. Again, I used dozen as an example of a mole. It's just a number or a word that means a number when we're counting. Our second unit factor from Chapter 3 was 1 mole equals the molar mass in grams. And that molar mass number comes from our periodic table, where it's different for every element or compound. And then our third one was the mole ratio. Now, the mole ratio came from our balanced chemical equation, and that's how we can compare moles of one chemical to moles of another chemical in a certain reaction. Remember, balanced chemical equations are just like recipes. And so we use those 3 unit factors to do some math, convert between atoms and grams and moles and grams to grams, all kinds of things. So in Chapter 4, what we're going to do is pick up right there. We're going to learn some new categories of chemical reactions. So we know 3: combination, decomposition, and combustion. We're just going to add some more to that. We're going to look more closely at our aqueous solutions. So when we were balancing equations in Chapter 3, every chemical had to have a state of matter after it. S for solid, L for liquid, G for gas, or AQ for aqueous. And all I said in Chapter 3 was aqueous. It means it's dissolved in water. And then we just moved on. So in Chapter 4, we're going to look, first of all, we're going to look more closely at aqueous solutions and what that means is happening in the chemical reaction. We're going to add more categories of chemical reactions to our list, and we're going to look at these aqueous solutions, and there's a new unit factor, a new unit that goes along with them, which is called molarity. So we're going to learn about that. And all of this is going to build on top of the things that we have already done. So we will still be using like the mole ratio and molar mass. We'll still be balancing chemical equations. We'll still see combination, decomposition, combustion reactions. So Chapter 4 and Chapter 3 are very much linked. It would just be one huge giant chapter, way too big for us to worry about all at once. So they were split in half. And here we go. So we're going to start with reminding ourselves of some vocab. So solutions. Solution is a term that we talked about back in Chapter 1, but at the time we were mostly focused on calling them homogeneous or homogeneous mixtures instead of the word solution. They mean the same thing. So back in Chapter 1, we took all matter and broke it into 2 main subcategories: pure substances or mixtures. And then with each of those categories, we could break it down even smaller into 2 more subcategories. So under pure substances, there are elements and there are compounds. Under mixtures, there are homogeneous or homogeneous, however you want to say that, and heterogeneous or heterogeneous mixtures. So homogeneous mixtures are when we take the components, the different pure substances that we put in the same container, and when I mix them up, it's evenly mixed. It looks the same at the top, the middle, and the bottom. So a solution is just another way to say a homogeneous mixture. From now on, we're going to use the term solution instead of homogeneous mixture. That was a really straight line. So again, a solution, it's just you have 2 or more pure substances in the same container, you mix them up, and they're evenly mixed. We're going to call that a solution. So more specifically, an aqueous solution, which we'll see here in a second, just means one of the components is water. We mix it in water. Okay, so we've got some vocab, though, for these components. If we've got a mixture of a bunch of things, let's go with, I have 3 things, okay, that I mixed together in that container that hand is holding that's got blue liquidy stuff in it. Let's say there's water, there's copper 2 nitrate, and there's sodium chloride. Whatever, there's 3 things I mixed together. Of those 3 things, whichever one there is the most of, that is called the solvent. The solvent is the one that there is the most of. So in this case, it would be water, just because it's a lot of liquid with well, I'm telling you, it's water. Okay, so it's the one that there is the most of. If I had given you amounts of each of the 3 chemicals, you could look at those amounts and tell me which one is the solvent. For us, this chapter, almost always, for us, the solvent is going to be water, because in the chemistry that we do in general chemistry, water is the thing, it's the most abundant solvent we have. But like if we look at the air is a homogeneous mixture, which makes it a solution. Nitrogen is the solvent, because in the air around us, there is more nitrogen than any other gas, and it's an evenly mixed mixture, so nitrogen is the solvent. So it doesn't have to be water, it's just for us, it will mostly be water. Now, all the other substances. So in this mixture, with that picture, I said it was water, copper 2 nitrate, and sodium chloride. Well, so water is the solvent. Check. So that means copper 2 nitrate and sodium chloride are called solutes. Those are the ones that there aren't the most of that chemical. So there's only ever one solvent, but there can be multiple solutes. So you can have a mixture of 47 things. Of those 47 things, one of them is the solvent, and you would have 46 solutes. Okay, so the solutes, there's less of them than there is of at least of one other thing. So when we're looking at aqueous solutions, again, all that means, aqueous stands for water. So water is the solvent. Now in an aqueous solution, you might think, well, they're going to be clear, colorless liquids. Well, and just so you know, clear and colorless don't mean the same thing. Colorless means when you look at it, you don't see a color at all. It's not on the rainbow spectrum. There's just no color. It's not white. It's not black. It's just there's no color. Clear means you can see through it. So in this picture, that solution that's in that beaker right there is green. So it's not colorless. It's green. And it is clear because I can see through it. Think stained glass windows. Don't stained glass windows have colors, but you can see through them. So they have a color and they are clear. So aqueous solutions are going to be clear, but they may not be colorless. Just that last picture, it was blue, okay? And this one, it's green. You can have different colors, but aqueous solutions should be clear. So let's look at what's happening when I mix stuff in our example again, we're going to stick with water. So if I have an ionic solid, we learned how to name different compounds back in chapter 2, ionic, binary molecular, and acids. So an ionic solid would be an ionic solid, or a solid that has a positive charge, a cation, and a negative charge, an anion, together. In this picture, it's sodium chloride, where the purple spheres are sodium and the green spheres are chloride. And what happens is when we mix it with water, well, table salt dissolves in water, right? So what actually happens? Well, when you take that table salt and you mix it with water, you don't see those little white crystals anymore. It's like they magically disappear. They don't magically disappear. Instead, what they do is it dissociates. So what it means by dissociates is the sodium ion and the chloride ion separate. So there's the sodium ion, one sodium ion, and there's one chloride ion. And you see how around each of those are a bunch of water molecules. Now they are arranged in certain ways. So like the sodium ion, if you see that the water molecule, the red atoms are the ones kind of facing the purple. And in the chloride ion, the green one, the white atoms are kind of the ones facing the purple. And it's all about opposites attract is what's happening there. But what's happening is that big crystal of sodium chloride, that is made up of a lot of very tiny sodium ions and chloride ions. So when it gets mixed with water, they break apart into their individual pieces, and the waters kind of carry them around. So that's called the waters when they're surrounding them and carrying them around. It's being solvated by the water. So the water being surrounded by the ions keeps those ions safe and happy and away from each other. So what happens is that little tiny crystal of sodium chloride just breaks into its tiny pieces and stays separated from each other. That's why we don't see those chunks of salt floating around when you mix salt and water. They are still, all the pieces are still there, they're just broken apart. And just as tiny individual ions, they're too small for our eyes to see, so we don't see them anymore. So it looks like they disappear. So ionic solids, this is what happens when we add them to water. They dissociate. They break apart into their pieces. Okay, so we're going to continue with our vocab portion here. So electrolytes are things that when you add them to water, they dissociate. So you've heard the term electrolyte probably from TV. Think like Gatorade or Powerade or just any of those types of things. They talk about, you need electrolytes so that way you can run fast and jump high and all that stuff. So electrolytes are just things that when they dissolve in water, they dissociate into their ions. Now they aren't lying. Electrolytes are important for our body, but they sound fancier and sciencier when they say it on the Powerade commercials than here. A non-electrolyte is just something that when it dissolves in water, it does not dissociate. So in this picture, okay, so these are waters. This big thing is not a water, right? It looks different. This is a non-electrolyte because when it's mixed with water, it's very clearly mixed with water, right? There's waters around it. Notice how it stays together. It didn't break apart. In that last picture, this was my chemical, and it is an electrolyte because when I added it to water, it broke apart into their pieces. So what I want us to practice, so number one, we're going to need to know these terms. Okay, just because it's a non-electrolyte does not mean it doesn't dissolve in water. It may still dissolve in water, but when it does, it just stays whole. I'm going to give you this chemical, and I'm going to tell you, because you don't know yet how to tell, we will learn that this chapter, that this is an electrolyte. Oops, I don't know what I'm doing. This is an electrolyte. So I put it in water, and it's going to break apart into its ions. So what we're going to do here is I want us to figure out, well, what are the ions? How many ions are there in this one molecule? It's kind of like we're doing chapter 2 again, only backwards. Instead of putting the ions together to make a compound, we're going to take the compound and break it apart. So, well, this is made up of magnesium. Now, when we're writing it as an ion, we are going to have to include the charge because ions have charges. So we're going to have to look back at our periodic table, find magnesium, see that it's in group 2. Do you remember what charge the atoms in group 2 have when they are ions? 2+. And then there's chlorines. Now it's Cl2, but remember when we're doing an ionic compound, remember when we were putting them together, we made little tables kind of like this. There are 2 chlorines, so I'm going to write them as separate things. Now, what charge do they have based on where they are in the periodic table? They're in group 17, so they have a -1. So when magnesium chloride is added to water, it's going to break into 3 pieces. It's going to break into its magnesium, and I'm just going to put a plus sign between them. I could write Cl- plus Cl-. I could totally do that. Or I could combine those. But when I combine them, I'm going to have to say 2 Cl-. Remember in chapter 3, when we were writing our balanced chemical equations, there's a difference between subscripts and coefficients. These are 2 different ions that are not attached to each other, which is why the 2 goes out front. If they were still attached to each other, which I know it looks like they are up here, but this is when it was a whole molecule. When we add it to water, it breaks apart. So if they were still attached to each other, we would see a subscript. The only time you're going to see subscripts when we're looking at electrolytes are the polyatomic ions. The polyatomic ions are ions themselves, so when they dissociate, they don't break down even smaller. So let's do sodium nitrate, and I'm telling you, I'm going to be lazy, I'm going to write E there, which stands for electrolyte. So it's an electrolyte. So I add it to water. When I add it to water, it's going to break into its ions. Well, I see sodium. What charge should sodium have based on the fact that it lives in group 1 on the periodic table? +1. And then nitrate. And nitrate's one of the polyatomic ions, so we need to just memorize, we need to know that it's got a -1 charge. And if we look at that, there's just 1 nitrate there and 1 sodium. So I'm going to draw this to separate them. So when this is added to water and dissociates, I get these 2 different ions. Now, nitrate is not going to break down any further. That's why we need to know the polyatomic ions, is to recognize them. So it truly is important for you to actually memorize those polyatomic ions. They're not going to go away. So these would be the ions that we would get for this electrolyte. Now, if I had something that was a non-electrolyte, I guess I should change color for that. I'll go up in this corner. And I would, for right now, again, you don't know how to recognize by looking at it. I'm going to write Ne for non-electrolyte. When this gets added to water, if it's a non-electrolyte, it does not dissociate, which means... Why are you doing that weirdo pen? It stays the same. It's not going to break apart into pieces. It's just going to stay the way it is. Okay. So let's look at how we can classify, how we can tell by looking at something. Is it an electrolyte or a non-electrolyte? So we're going to come back to this table here in a minute, because actually I need to do one more vocab term first, because we see 3 categories. There's a strong electrolyte, a weak electrolyte, and a non-electrolyte. Well, for non-electrolytes, I don't have a good we have a good definition, but I don't have a good way of determining them, other than it's a lot easier to determine if something is a strong electrolyte or a weak electrolyte, and then everything else is a non-electrolyte. So let's look at these definitions, and then we'll put it all together here. So a strong electrolyte. Strong electrolyte and weak electrolytes are both considered electrolytes, which means when you add them to water, they dissociate. The difference between the two is how much they dissociate. A strong electrolyte, you put it in water, 100% of it, all of it, dissociates into the ions. There are no compounds or molecules left. It's all completely ions. A weak electrolyte, when you add it to water, some of it dissociates into its ions, but some of it stays together as a compound. So it has to be considered an electrolyte because some of it dissociates. Non-electrolytes do not dissociate at all. But that's why we have two categories. And actually the difference between these is kind of crazy. So a strong electrolyte, 100% of them dissociate. All of them break into their ions. Weak electrolytes, for the most part, 1 to 4% of them dissociate. So it's kind of an, I can't say it's all or nothing because it's not. If it was all or nothing, there would just be electrolyte and non-electrolyte. But there's strong electrolyte, 100% of them, they're all ions, there's no molecules left. Weak electrolyte, a little bit breaks apart, but most of it stays together. And then we have our non-electrolyte, which doesn't break apart at all. Okay, so one way we could tell the differences between these, which I have never done it this way in the lab because I don't walk around with a light bulb in my back pocket at all times, but strong electrolytes conduct electricity really well. So one way to test if it's a strong electrolyte is you take the compound, dissolve it in water, and then try to run electricity through it and see if that happens. So one good way to tell if the electricity is running through the solution is to have a light bulb on the other end. So we've got the black cord is bringing in the electricity, and then you see how there's a gap between those. So in order for the electricity to go from here to here, it has to be conducted. And so if it's a strong electrolyte, the electricity goes right over there, no problem. And then it goes into the light bulb, and the light bulb's nice and bright and shiny. For a weak electrolyte, it conducts a little bit of electricity, like this much, whatever its percent is. So we can see the light bulb lights up, but not really well. Because it only gets a little bit of electricity. A non-electrolyte does not conduct electricity at all. So that's this scenario where there's no light at all, no electricity got through. Again, this is a great way to test it. It's just, I don't usually have this set up just with me at all times, but it's one way to tell. So, strong electrolytes, and I'm going to summarize all this here in a second. Things that are strong electrolytes. They are strong acids and strong bases. And on that table right below that, there's a list of the 7 strong acids and the 8 strong bases. Okay. So those compounds, those 7 strong acids and those 8 strong bases are strong electrolytes. Also soluble ionic compounds. And actually at the end of this, at the end of the day, it's really all ionic compounds. So acids are things we have looked at before. We recognized acids in chapter 2. That was the more confusing section of the naming, where we had the, if it ended in an "ide," it was a hydro something ic acid. If it ended in "ate," it was an ic acid. If it ended in "ite," it was an us acid. Remember we talked about the weird, like, it's like we're speaking another language with naming, and we kind of are. Well, all 7 of the strong acids start with H, right? That's how we can recognize something as an acid. Well, only these 7 compounds that start with H are considered strong acids. Every other compound that starts with H is still an acid, but it's not a strong acid. The strong bases, there are 8 of those, okay? And then ionic compounds, that was another category that we had. So soluble ionic compounds are super good strong electrolytes. But we're really going to kind of go with all compounds, or all ionic compounds are strong electrolytes. So I gave you a list of what the strong acids and the strong bases are, so we can tell that. And all ionic compounds, we could tell that based on the cation and the anion, but soluble ionic compounds, well, we have this set of solubility rules that we can follow that tell us, is it a soluble ionic compound? A soluble ionic compound means you add it to water and it dissolves completely. Okay, so we're going to come back and practice these rules here in a little bit. These rules are going to be things that we need to memorize, along with the 7 strong acids and the 8 strong bases. So again, these sets of rules tell us if it only works for ionic compounds, but if it is an ionic compound, we can use this set of rules to determine is it soluble or insoluble. So again, soluble means dissolves in water completely. Insoluble means you add it to water and it doesn't really dissolve. Okay, so let's break our 3 categories of strong electrolytes, weak electrolytes, and non-electrolytes. And we're just going to list what things fall under what categories. So again, strong electrolytes. Dissociate 100%. All of them break into their ions. And those things are the 7 strong acids. Go back a couple slides to see what those are. The 8 strong bases. And the soluble ionic compounds, which I'm going to write after that solubility rules. Okay, so let's list the things that are weak electrolytes. Things that are weak electrolytes, they dissociate I'm going to say 1 to 4%, but really the definition is less than 100%. And those are going to be the weak acids. So you're going to recognize a weak acid because it starts with a hydrogen, and it's not one of the 7 strong acids. There are hundreds, maybe thousands of weak acids. So we're not going to memorize the weak acids. The only way to tell apart the weak acids from the strong acids is to know all of the acids that fit in one of the categories. And then the other ones fit in the other category. Well, do you want to memorize hundreds or thousands of weak acids, or do you want to memorize the 7 strong acids? Well, it's way easier to memorize the 7 strong ones. And as long as you recognize, though, you're like, oh, good, that's an acid because it starts with an H, and it's one of the 7 strong ones, so I know that it's a strong electrolyte. That's an acid because it starts with an H, and it's not one of the 7 that I memorized, so it must be a weak acid. And then for non-electrolytes, they're everything else. So the molecular compounds. And really for us, if it's a solid, a liquid, or a gas, it's going to be a non-electrolyte. Okay. If it's aqueous, it's going to be one of those 2 for us. Okay. So we'll come back and we're going to be practicing this a lot. We're not done with this part yet. So I'm going to add a 4th type of chemical reaction to our chart. Our charts so far are combination, decomposition, and combustion. We learned those in chapter 3. Combination. We take more than one element or compound and put them together into one compound. That's a combination reaction. Decomposition. We start with one compound and we break it apart into more than one element or compound. And then combustion, that's when we take something plus O2 gas, arrow CO2 gas plus H2O gas. That means we're burning it. Okay. So a precipitation reaction is our next thing. So first we have to define what a precipitate is. A precipitate is an insoluble solid that we form in a reaction. Okay, so we make a reaction that's aqueous, and one of our products is a solid. So in this one, lead 2 nitrate is mixed with potassium iodide. Both of them are aqueous. And then we make 2 products, and one of them is lead 2 iodide, which has a solid after it, and the other one is potassium nitrate, which is aqueous. So this is the precipitate. And a precipitation reaction is a reaction that makes a precipitate. So what you're looking for is you start with aqueous things and you end with at least one solid thing. So we're looking at states of matter is what we're looking at here. So aqueous, aqueous, solid, aqueous. Because of the fact that we started with an aqueous and we end with at least one solid, that would be a precipitation reaction. If this one had also been a solid, still would have been a precipitation reaction. We just would have had 2 precipitates. If this one had been aqueous, this would not have been a precipitation reaction. You have to have a solid as a product if it's a precipitation reaction. So we're talking about solubility. Just to be clear on this, when we're looking at solubility in this chapter, we're just saying, yes, it dissolves in water, or no, it doesn't. It's actually a lot more complicated than that. So when I'm at a restaurant and I order a drink, I usually order sweet tea because I like sugar. So at the restaurants that don't have sweet tea, if I just get, unsweetened iced tea, and then they usually bring me those little packets, with sugar in them. So my unsweetened tea, I tear off the sugar packet and I pour it into my glass and I stir and I stir and I stir. Now, I know that sugar dissolves in water, and I know sugar dissolves in tea because that's a thing that I make all the time at home. But at the restaurant, when I pour that sugar in, not very much dissolves. Most of it settles on the bottom. Okay. But sugar dissolves in water. I know that to be true. But there are other things that impact that. One of those is temperature. It's cold, right? There are ice cubes in my glass. So that's going to mean less sugar can dissolve in the water. We're not going to get into the details of this. For right now, as far as we're concerned, solubility is a yes or no question. Yes, it dissolves. No, it doesn't. But we will learn in general chemistry too, that there are other factors at play here, like the temperature. And it's also even a little bit more detailed than that, because sugar, I might be able to dissolve 10 grams of sugar in 100 milliliters of water. But with salt, maybe I can only dissolve 2 grams of salt in 100 milliliters of water. There's a number that goes with how much can you dissolve, and that number changes based on the temperature, and that number changes based on the chemical. So again, we're not getting that detailed into this for right now. It's a yes or no question for us, but I wanted to point out that, oh my gosh, yes, there's more to solubility than just yes or no. We're just not going through that. Okay, so there's our solubility rules. Again, we saw these earlier. I just kind of breezed over them. Solubility rules are a way to determine, yes, something dissolves in water. And by solubility, by something, I mean an ionic compound. So yes, an ionic compound dissolves in water, which means it's soluble. And if it's soluble, then that means, so soluble, in its chemical reaction, it would have an aqueous after it because it's dissolved in water. Okay. Or this table can tell us, is it insoluble? I'm having spelling problems here. Which for us, that would mean it's a solid. So I know it's tricky because soluble starts with S. But soluble means dissolves in water, which tells you it's aqueous. And insoluble means it does not dissolve in water, so it sits at this bottom like a solid. So think like sand in water. Sand is insoluble in water. It does not dissolve in water. So these rules, the way I have these rules set up, when you look at an ionic compound, and you'll recognize that it's an ionic compound because it has a cation and an anion, a positive charge and a negative charge, and you have to only use ionic compounds with this table. Notice it very clearly lists ionic there. This only works for ionic compounds. This does not work for acids. This does not work for molecular compounds. So for ionic compounds, you recognize it's an ionic compound. And then to use this table, what you're going to do is you're going to look at the anion, the negative charge part. And then over here in this column are a list of anions. So you're going to look at the compound, figure out which of these things is the negative charge, and then find it. So if I found it and it was a hydroxide, okay, well, the hydroxide is under this insoluble ionic compound heading, which means most compounds that are hydroxides do not dissolve in water. Most of them are solids. But then over here, if I keep going over, it has a list of important exceptions. So hydroxides in general do not dissolve in water, but there are some that do. And those are the alkali metals, which I'm going to list up here. Well, the alkali metals are group 1, except not hydrogen. Hydrogen's not a metal. Okay, so group 1, sodium, lithium, potassium, rubidium, cesium, those. Okay, so sodium hydroxide does dissolve in water. Hydroxides generally do not, because it says they're insoluble, but it's an exception. So sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, those all dissolve in water. Plus calcium hydroxide, strontium hydroxide, and barium hydroxide. Those all dissolve in water. Okay, so that's how I can figure out, is it insoluble or soluble? You find the negatively charged thing, check the rules to see if it's an exception, go from there. So if I look up here, I don't want to do the hydroxides anymore. I want to do, like I saw it was a chloride. Okay, so I looked it up, and it was a chloride. So chloride is under soluble. Okay, so that means most compounds that have a Cl- in them are soluble. But there are exceptions: silver, mercury 1, and lead 2. That means silver chloride is insoluble. Mercury 1 chloride is insoluble. Lead 2 chloride is insoluble. So the exceptions tell you which ones don't fit this category that they are in. So let's practice, okay? Here's 3 compounds. One of them I gave you the name, the other 2 I gave you the formula. If I give you the name, you need to write it as a formula first. So cobalt 2 hydroxide, we've got to turn that from formula into name. So yes, what we learned in chapter 2 is important and you need to remember it. So cobalt, we have to remember that is CO. That 2 in parentheses is telling us it's a 2+ charge, because if we find cobalt on the periodic table, it is not in a group that I know its charge. Hydroxide, it's a polyatomic ion. We'd have to remember it's OH-. So let's put that together. Cobalt 2 hydroxide will be 1 cobalt, 2 hydroxide. So I'm trying to decide if this is soluble or insoluble. So what I need to find is the negative charge. So that is a hydroxide. So I'm going to come back over here. It's a hydroxide. Okay. Hydroxides are insoluble except the alkali metals: sodium, lithium, potassium, rubidium, cesium, calcium, strontium, barium. Okay, so what was ours? Oh, it was cobalt. Is that one of these? No, it's not one of those. So that means it is not an exception. Oh, how I made those little dots. It's not an exception, so it is insoluble. So, pen. It is insoluble, which means in a chemical reaction, it would be written cobalt 2 hydroxide solid. Solid is standing for insoluble. Okay, so let's try it again. Let's go to the second one. Barium nitrate. So nitrate's the negative charge. So I'm going to go back to the other slide. I'm going to find nitrates. I'm going to erase all my things. So I find nitrate. Okay. Nitrate is under the soluble heading. So most nitrates are soluble. I go over to the exceptions. There are no exceptions. What that's telling me is all nitrates are soluble. I don't care what it's paired with. Everything that has a nitrate is soluble. So this is soluble, which means in a chemical reaction, it would say barium nitrate aqueous. Okay. So last example, phosphate. This is an ammonium phosphate. So I'm going to go back to my previous slide and find phosphate. Oh, there it is. Okay, let me erase this. Try to erase that. Okay, so phosphates are in the insoluble section, right? So that means almost everything that's a phosphate is a solid. The exceptions: compounds of ammonium, which are NH4+, and alkali metals: sodium, lithium, potassium, rubidium, cesium. So does our compound that's a phosphate contain any of these things? Well, if we look backwards, it has an NH4+. Isn't that one? So it's a phosphate, but it contains ammonium. So it's an exception. Well, phosphates are insoluble, so the exception means it is soluble. So this is soluble, which means when we wrote it in a chemical reaction, it would have aqueous after it. So insoluble, soluble, soluble. Yay! We're going to be practicing these solubility rules for the rest of the chapter, but hopefully this got us started.